on page 29, where it says use the proof of at least two left inverses of
Yeah.
the injective functions there
Yeah.
from the table 3.
Yes.
I had problems with the one that concerned the subset, where they say A is the subset of B, the last line of the table there.
Ah.
And it uses a certain, that simple, I think it's notation there.
Yeah, that is the yes. Uh, that is called a hooked arrow. It looks like a hook, right?
Yeah, it looks like a hook,
Yeah.
a fishing hook, yeah.
Uh, that is usually the symbol for denoting the inclusion map. So remember the inclusion map. 1 minute. The inclusion map. If you have A, you can see my screen, right?
Yes, Doc.
So the inclusion map I also denoted by IA, I think. Yes. The domain of that was A. I wrote it like this. And if you remember, it was taking X to X itself, right? Right? And so, for instance, so it is doing nothing. It is called the inclusion map because it is just restating again that X is a member of A. So IA of X is, so this is not the identity map because for the unless A is equal to B, this was one of the first examples of functions. Now some people also use this symbol, and it is only used for inclusion maps to say that this is an inclusion, to say, so as if this symbol of subset has been elongated into an arrow. So often also people use this, so that's the symbol. So now what's your problem? Is the problem only with the symbol or the left
Now,
inverse?
let's just go on with the example, I think.
To find the left inverses.
Yeah, of the left inverse of this one.
Okay.
Because when I got that symbol, I just got lost. I didn't understand.
Oh, okay. Okay. But you see, you can immediately see how does this symbol look like. This is actually saying that if you have A over here and B over here, and if you think of A as this subset on this side, then it is like this. Right? Distinct points of A are exactly taken to this. And so on. But no point over here has a pre-image. Right? Is this the stock? Do you get the stock diagram?
Yeah, looks like a stock diagram.
Yeah. So this is the stock diagram of any inclusion. If this is the subset A, this side. So these are all the members of A, and this is the whole set B. Then the inclusion map stock diagram looks like this, right? So if this is the picture, but things over. So it says it is injective, the diagram. So this is your inclusion map. Now to find a G, you want to find a G which is its left So you want to find a G such that G composed IA is 1A. Right? So you come from here, come to this point. So if you start from here, you have to go here. There is no other way to define your G. So Gx has two options. One, if x is in A, and otherwise if x is not in A. So what will you do if x is in A? There is no question. There is no extra question.
You get back to x.
Yes, so you give back x. Now for these you have to choose a particular element, say. You choose a particular element, say A. So choose A from A, and then you can send all of them to A. Right? So if x is, all these points are taken back to A, this point. So then you see, G composed IA is obviously the identity. And as you vary your choice A, you can if you make this, if this is another point B, so you could write GA is this and GB is so you see both of them are candidates for both of them, and they cannot be equal because GA, if you have, obviously you know that if A is a proper subset of B, if this happens, then your inclusion of A is not the identity map. So this is the identity map in the only case when A is equal to B. But when A is equal to B, there is only one choice for G, because there will be no such elements like these. So everything, so this place is empty. So every point has so that is the identity map, and that is therefore invertible automatically, right? So the moment you have this and you have one point here, at that point, and if your set A has two members, at least two different members, you have two different choices for, so you can immediately see this. So if A is a proper subset of B and A has at least two elements, then GA and GB are two distinct left inverses, are distinct left inverses. Okay? Clear?
Yes, Doc, I think it's clear now.
Okay. So could you do the others?
Yeah, I will try.
The others should not be a problem. Yeah? Because
Only that for the cause restricts the domain.
you're coming broken.
Because okay.
You're coming broken.
Sorry.
You're broken. I cannot hear you.
Wait here. Hello, can you hear me now?
Yes.
Yeah, no, I was simply saying that the cosine function, you only domain that is restricted there.
Yes, obviously.
If the domain is not restricted, it will neither be an injective or a surjective function.
Yes. So over here I have taken the cos function like this. It is from 0 to pi by 2. Right?
Yes.
So that is my cos function now. So if you try to draw the graph, it looks like this. So here it is 1 and so something like this. Right? Clear?
Yeah, it's clear.
So you see, it's if you draw the graph, you can immediately see you have done this in your calculus, that this function is a graph of the cos function, and this is one-to-one function. It is obviously a one-to-one function. But the problem is that your codomain is R, right? So that's where, if you try to draw the stock diagram of this, it is again something like this. The diagram again looks like this. So where this is the part that is over here, which is the range of that function, the only difference is that, okay, so you see, that's my exact point to say. The stock diagram again looks like this. Where, so this is the picture, and if you see my case, which one is it? Case 5b, the diagram 5b. If you see that, this is exactly the picture. So you have a subset of the codomain, which is the range, and if you look into that part only, the stock diagram looks like exactly one. Everyone has only one, right? It just sticks like this. And there is a part where there is nothing in the stock. So for injective maps, you therefore know finding this is very much similar to finding the solution for this. That's why I said last time that we will slowly get imbibed with the idea. Well, diagrammatically, if we see that injective maps are essentially something like this, you can say a stereotype picture is like this of this inclusion. So that's the stereotype of an injective map. So this is an injective map. So you know, for such diagrams, if you are given this side, how do you get hold of your left inverse? This side. Okay? The same argument, the same thing, and so on. Now, we try it out again. So, where were we last time? If you have any further questions, or should we proceed, or what do you say? Yes? What do you say? Should we proceed? Or where was I last time? I think I finished this.
Let's proceed.
Okay. So I think I was, where was I up to? I was up to, I think we did up to bijection, right?
Yes.
Yeah. So, and I spoke a little bit about natural bijections also, right?
Yes.
Okay. So, if we look at that, then remember what we said was, so what turns out is, so for a function, it has a left inverse, so that means there is a function g from b to a such that g composed f is identity of a. This is the same thing as saying it is left cancelable. So which means fx, fu, if v implies u equals v, and it is the same thing as saying that fx.
Doc,
Yes.
I think the network, I'm not sure, but you're breaking up.
Oh.
The noise.
Oh, okay. Yeah, I'm also seeing that. I don't know why. So is it a little better?
Yeah, it's perfect now.
Yes, it's much better.
Okay. Now there's the other one is as if some kind of a so this means that you have G now again from B to A, but this is the right inverse. This is the same thing as saying it is right cancelable. That means U composed F is equal to V composed F. It implies that U is equal to V, and this means F is surjective. And there's the third option, which is both. Now here, the first thing that we observed therefore is, so if it has, so I am now saying that it has a left inverse and a right inverse. So if that is the case, so G composed F is G is the left inverse and H is the right inverse. Well, this is something, if you have done group theory, groups, you know, now you can show, because it's an associative thing. So it turns out that G is equal to H. So why? Well, G is equal to G composed 1B, but this is same as G composed F composed H, which by associativity is again this, which is 1A composed H and which is H. So if it has a left inverse and a right inverse, then G is equal to H, and it is the unique. So in this case, the inverse is unique. And hence, we write it like this. That's why we write it like this. Okay? And if you remember, initially, although for relations, I also used F inverse, but then I changed to the symbol F op. And that's the reason, so that there doesn't exist any confusion. So when F is a function, so when F is a bijective function, so you know F is a subset of A cross B, and F inverse, its inverse is a subset of B cross A. That is also a function. And the relation, the relation is F op. It is just xy belongs to F if and only if phi x belongs to. So that is the, so what is, how do you define F inverse? Xy belongs to F if and only if yx belongs to F inverse. So which is exactly what we said as the opposite relation, and that becomes in case when f is a function, that becomes the inverse function. So it has a so now we come to another part of the story. So why did I say this? The whole issue is that I want to show that any function can be expressed completely in terms of a injection and a surjection. So what I am going to say is, so suppose you have a function f. Okay, now look into this. I think I said it, the range. You remember this set. This is the set of y, set y belongs to B such that y is equal to fx for some x in A. So you can think of this alternatively being written as f of x as you change your x over A. So obviously you have one function coming from here which I write as f prime because I don't have any other way. And what does f prime do? F prime is this function so it takes x to fx. So obviously, as you can see from its definition itself, f prime is surjective. And you have, this range is already a subset of B. So you have the inclusion map of the range. And this inclusion is obviously injective. And f is nothing else but the inclusion of the range of f composed with f prime. So you see, f decomposes as an injection and a surjection. Remember, because we write the other way round, we often say f decomposes or f factors as a surjection followed by an injection. So that means it is injection composed as surjection. So f factors as a surjection and an injection. And there is something nice about this. There's something nice about this. This is in a sense unique. This factorization in a sense unique. Now that's what I am going to show now. But to do that, I need first an auxiliary result. So this is an auxiliary thing that I need. So let me call it a lemma. consider, suppose this diagram. Where E is a surjection and M is an injection. Okay? Suppose if you have this, then, so if you have this, then there exists a unique function such that so I'm saying there exists a unique function like this which fills up this diagram, this diagonal. So there exists a unique function W that fills this diagonal such that this composed, this is V, so V is M composed W and U is W composed. Now let's see how do we prove this. So let us redraw this. Now I know since E is injective, let's try. What are the things that are given? This one is surjective, so it will have a right inverse. So I will have an E prime like this, right? Such that it's the inverse. So E composed E prime is equal to identity of Y. Let's now try and see. So if I have some way to go from Y to X and I compose, so does it happen? So let me try and see if this works. So take W equals to, say, what is it? U composed E prime. I didn't say, when I drew this, I should have said such that this commutes, such that surjection, this is an injection, and obviously M is an injection, and V composed E is equal to M composed U. So this diagram initially commutes. So now let's try. So what do we have? We have found out a possible answer for W. So let's try. So V composed W, this is V composed U composed E prime. Now V composed U composed U prime. What did I make? Sorry. So not V composed W, sorry, W composed E is U composed E prime composed E. But remember, this is identity, so this is U. Okay. Now let's try the other one. Good. So one I have found out. So let's try this. M composed W. So this is M composed U composed E prime. See, I have already dropped using the brackets because I know it is only one way out. But M composed EU is equal to V composed E composed E prime. So that's V. Well, we are done. Now the question is, why should this be unique? There is no way, because we know already by this time, we know that there are several ways of the right inverse E prime is not unique. That's true. But we have something more. If W prime, so we have found out one. If W prime from Y to P be another one, another function such that U is also equals to W prime composed E and V is equal to M composed W prime, then taking any one of them, then say U is W prime composed E and that is also equal to W composed E, but E is right cancelable, implies W prime is equal to W since E is right cancelable. Okay? So you see, you take nothing. Do you see the proof? The beauty of the proof, it doesn't involve, you have defined a function in a, so firstly, before I finish, so W prime is, so even if you take another choice of the right inverse C prime, some magic is done by this composition. So between several such choices of this right inverse, when you compose it with U, it gives that unique map over here. Clear? So that's where the magic works, this commutativity works, and that gives you the proof. Okay. Now how do I use this? Let me show. So what did I say? You started off with your map A to B. I can go to another page. So you started off with your map. So this was your so this was your function. So this was your I of range of F, and this was your F prime. Remember, this one was surjective, this one was injective. Now I am saying that suppose there is another way to do this. So suppose you have another factorization. Say T and this. So this is surjective and this is injective. Okay? So then what happens? I shall use I'll write this, redraw this as a square. So this means This you have drawn like this. But you can also draw this like this. This is your M and this is your E. Remember, the whole picture was, remember this picture, it says, remember this one, the top was surjective, this one, the bottom was injective, and you had this square to commute. Then from the top right to the, so you have this diagonal filling. Okay? So, here, this is your F, so is this. So this diagram commutes. So your lemma says that there exists a unique map, W. Right? But now, observe another thing. This is because there exists a unique map W such that your WF prime is equal to E and M W is equal to this I of range. But observe again, if you just if you just think of, how do you say, if you rotate this diagram again so that this becomes the top and this becomes the bottom, then again this is a surjection, the top is a surjection, the bottom is an injection. So your lemma says again that there is another map like this. So you have another map, right? W prime. And what does this do? So your W prime E is equal to F prime and your W prime image. So this is your F. Now let's see what happens. Your E, so let's take these two equations. So E is equal to, so let's see, W prime E, this is equal to W prime, because you told me this is F prime. Right? What am I doing? Yeah. F prime is equal to this. But you told me that F prime is equal to this. What am I doing? No. Yeah. I'm right. Okay. So I'll use these two equations. So first, as if multiply this one by W prime. So F prime is equal to W prime E, which is therefore W prime WF prime. Right? Similarly, so what does this say? But I can extend this equation a little more. F prime is also equal to the identity map of this composed F prime. And remember, F prime was surjective, so it's right cancelable. So W prime W is equal to the identity of the range. So it turns out this. Now a similar picture. So E is equal to WF prime, but F prime is WW prime E, and E is again same as identity of T composed. So this tells us that WW prime is equals to the identity of T because it's right cancelable. So therefore W and W prime are it's a bijection and this is. So therefore you see, if you have any other factorization of this, it tells us that this set T is nothing else but a renaming. So there exists a unique bijection between them. So in that sense, the factorization, is unique. Means, so you can take F to be this surjection followed by this inclusion map. You can remember that, but you can also say any F is a surjection followed by an injection, and that means that this T that you have taken is essentially in bijective correspondence. Okay, so this is nothing else but a renaming of the members of the range. So essentially, you don't have to remember. So what does this tell you? You don't have to remember this particular explicit factorization which I took. You can take it to be a factorization by a surjection followed by an injection, and that's it. That does the job. Okay, now let me stop. Let me see where did I lose you? Do I have you? And so on. Yes. Now it's up to you to say. Yes? Am I alone? Or
No, Doc, you're not alone.
okay. So what do you say?
Doc, can I ask a question?
Yes.
This section of the work that we're now covering, is that part of the surjective, or is it the bijective
No.
functions?
It is the next one which is called factorization of functions.
Oh, it's number 6, yes.
Yeah.
Okay, got it. Thank you, Doc.
Now, where am I? I mean to say, did you understand? Where did I miss you? Where it is difficult? Let's look into that.
On my part, I think I am more comfortable with these commutative diagrams. It makes the whole setup, I think, easier.
Good.
I think, I'm comfortable with the commutative diagram. They are clearer.
Good. Next. Yeah, I'm going to say something. But next.
Also, now, Doc,
Yeah.
if we look at proposition 6.2.
Okay. What is
Which
it?
is
I don't have it open.
Page 33. I'm just trying to relate.
Page.
Page 33.
Okay. Yeah.
There we also have a commutative diagram.
Yeah.
It talks about if superscript S or to the power S. How do we relate? What would that mean? We know what is S. Well, we know what is F. But what is this FS?
Which one, FS? Ah, okay. I just wrote that fs to denote what I did over here as f prime.
Okay.
Yeah.
Okay. F prime. Sure.
Yeah.
Thank you.
You see, okay, then the next question. The next question, or should I say something more?
Yeah, I think you can continue, Doc.
I'm comfortable so far.
Okay.
Thanks.
Now observe the one thing of this, what I did in this proof and so on. I never ever utilized, except in this case. In this place, I utilized internal, so explicit description of this f prime, and I utilized this explicit description of the range of f. Now, this is where and obviously therefore this inclusion function, I explicitly used the elements. Otherwise, if you see, I have utilized nothing else but equations and equations. So I have just used functions. Now, so there is no use of explicit use of how this function e looks like, how this function u or v or m looks like. I have only used the properties that e is a surjection, m is an injection, and this ve is equal to mu. And then utilizing the fact that since e is a surjection, there shall be a right inverse and so on. You could argue what would happen if I also know that m being an injection, it also has a left inverse. Sure, it has a, so it has a left inverse, yes, correct. It has a left inverse, that's right. But that doesn't lead me anywhere, okay, because now I cannot go, yeah. So you see why I chose the right inverse of E, because I wanted to find a path from Y to P, okay, that's what the proof is saying. I have to find a path from Y to P such that the full diagram comes. So there is only, so that's why I didn't consider this left inverse of an injection, although it exists, and I only considered the right inverse. So I started off with it. And then voila, it turns out that this u, using this commutativity of this ve is equal to mu, it says whichever right inverse may I take, this u does a magic. When you compose it with u, it becomes unique. Okay? So that's exactly what it says, what the proof does, without going into any explicit calculation. So something to be observed, no explicit calculation. Only existence of functions, composites of functions, and their equations. So that is only used in this. Okay. Now the next part is, I already had a factorization. This part used the explicit. This was done explicitly. Okay. Now I said that, well, is this the only way? To show that, I have now shown that, well, if you had any other expression of f, so here it says that f is a surjection followed by an injection in one way and a surjection followed by an injection in another way, then this T and range of f are in bijective correspondence. So what is the end story? The end story is, so when we say this uniqueness this uniqueness is only up to the property what is the property? That f factors as a surjection followed by So you see, there are two sides of the coin. If you use explicit, if you prefer the explicit route, then things become very, very strict, very, very strict and very, very restrictive. There is no question of like this, because then if you don't allow anything other than explicit things, then this is the only one and the only way of writing f as explicitly, right? Now, when you focus on the property and you are so you are making a trade-off. Either you want that explicit description in terms of elements and what is being happening to elements, where it is going, what is the this formula for the function and so on. This is one side. So you have this big, when you want this explicit thing, you want all of these prescriptions to be properly stated. On the other side, property level, you are saying that, well, f looks like a surjection followed by an injection. So equation wise, it looks like this. It looks like an ME, where M is an injective map and E is a surjective map. The moment you say this, you don't actually pin down this one, but you say, if you have anything else, then you have pinned it down up to a bijection. This T and this range, these sets are not exact, T is not exactly range, but T is, well, something in bijective correspondence. Now let me illustrate this with an example, so that will make it clearer. So suppose A is this, and say B is your finite sets. Give a big way to look into things, and suppose I say f looks like this. It takes a let me put this one is a little, let me put it this. A, it takes to say 2, B it takes to 2 and C it takes to 3. So you can see that the range of F is nothing else but 2, 3. Your F prime is therefore A, B, C to the range of F, which does exactly what you wanted. And you know what your indicator or inclusion that function does. This is this map from 2, 3. To B, which takes 2 to 2 and 3 to 3. But to be very simple, I can write, say T, say for instance to 2 things. I take E to be this one. It takes A and B to 0 and C to 1. Okay? And this is what I do. This is my M. It is this map from 0. So 0 is taken to 2 and 1 is taken to 3. So you see the obvious bijection this takes your B, or rather 2 to 0 and 3 to 1. That's exactly your bijection. That's exactly your bijection. Okay, so you see this, and well, this is 2 elements through 4 elements. This is obviously a much more simpler setup. But you can imagine that the moment you look into things which are up to this property, with this trade-off, it might be that you can get a better representation of T or whatever. So, what I wanted to say is, one side is explicit, where you need to say it explicitly, what is your range and what is that F prime and what is that. On the other hand, it is just saying by a property that it is factors like this. It's a surjection followed by an injection. Okay, and it's unique. Unique means in the sense that if there are any other factorization, then they are related by bijection. So the surjections are essentially related by. So you see, E is nothing else but WF prime. So you can therefore compute F prime from E or E from F prime. And similarly, you are saying that MW is this. So since W is just a renaming of the elements of T, from the knowledge of one you can compute the other. So computation is left up to this. So that's why that's the other story. Now, what is the moral behind this? The moral behind this says that to study functions, we therefore need to study. So there could be two different things. One which is given by injective functions. So two different. So it tells us therefore this factor. What does a factorization tell you? Since every function factors as a surjection followed by an injection, so it is enough to study. Enough to study surjections and injections separately. And then obviously bijections is the common ground of these two. So bijections is the not the common ground, is the, what do you say, is both. And that's all. That's so every function can actually, so the properties of every function come out from studying the properties of surjections and the properties of injection separately. So every function is in part surjective and in part injective. Okay, so it's going to be a mixture. Okay, so mixture of properties of surjections and mixture of properties of injections. And this is where we are going to enter next time. So what about injections? The idea is about counting or kind of comparing. What about surjections? The idea is about killing or gluing or identifying. So remember, this word identifying also came up while we were speaking with equivalence relations, so it has obvious connections with equivalence relations. So that is the whole story of surjections and injections. And interestingly, what turns out from all of this would be the following, that there is a duality between these two. So there is a duality. Between these two. Okay, and that would be the essence of our next few things, next few lectures. So that is where I'll stop today, and I'll open it for questions or discussions and so on. Yeah. Yes?
Not on my part. I'm fine.
Okay. Ayub?
Yes, thanks, Doc. Following.
Stanley?
I'm comfortable. In fact, it makes it clearer. Even the proposition that we had to do on page 29. I think based on what I've done here and the way I did it, I think I was not sure, but now, based on the methodology you used, I think I might have done it right.
Okay.
Proposition of 5.16.
5.16. Okay.
Yeah.
Yeah. Okay. Okay.
Do we have to hand it in? Because it's not in red, we don't have to hand it in. We're just doing it, it's okay, it's enough.
Yeah, you can hand it in. It's not a issue. Yeah.
Okay. Okay, thank you. Yep.
Thank you. Thank you. Yeah.
Thank you, Dr. Farsa.
Thank you. Thank you.
Thank you, Doc.
Thank you.
Good
Keep
night,
well.
everyone.
Keep well.
Thank
By
you.
the way,
Yes.
I was just one moment. Our exams will be sometime in January, February, right?
Yes.
Yes, Doc.
Now, to what date can we carry on? When would you want me to stop? When should we stop? You see, what I am wanting of you is, it would be pretty simple. I will actually place, since you are 3, even if you are 5, I would just place those 4 or 5 problems here itself. What would be the problem like? It would be something that you would develop, okay, from whatever, up to what place we study, from that place you should be able to develop that thing. You might also find it in the lecture notes that I am giving. You might find it somewhere else. You can consult between yourselves. But what I want is, when you are writing that, you should produce a document which is completely, what do I say? So everything that you require, every definition and everything that you require should be there. Okay, so it should be a self-contained document which explains that problem. So it would be a PDF file and so on and so forth. So given this, therefore, you might say that you might require more than 1 day. I agree, but the stipulation is about that I would actually kind of announce those problems, or because it is an examination, and so there are several things. So it will be essentially that problem up to a minor change. So possibly there might be a small little addition which can be done within a day. So given this mode of, firstly, would you agree with this mode of assessment? You might say that we have no other choice, but other than that, so it would be a problem which you should be able to solve using all possible resources from where we stop. Okay? What is
It's
it?
okay, Doc.
I'm
Yeah.
happy with it.
Yes?
No, I think that's fine.
Okay. So, when do you suggest that we stop? Should we stop, say, end November, or a little more? What do you say?
If we still need you, I think end November is fine. But if we still need you, I think we'll just inform you that we still need you, Doc.
No. Yes. I am always here. I am.
Okay.
I am always here. Yes. I am always available.
Would you kindly also give us some kind of, I don't know with others, but I think some kind of mock exam.
Why do you
Something
need a
which
mock
will give
exam?
us-
These assignments
which
that
will
you are
give us
writing.
an idea of what is happening.
Okay. These assignments that you are writing, these proofs, Make it a point that as if you are writing the proof, something like that. So you make it very, very clear, and you make it as if you are writing an essay. These assignments itself, that's your preparation. You see, I'll be when I give my feedback, I also say this is where it is the presentation, or you could have seen me writing back, would you mind submitting again with a proper presentation, right? And that's why I was doing it, because these submissions itself should tell you how you should submit. And you have one example is the notes that I have given, in a sense that you know that you have to kind of explain this thing properly. Now, this proper is why, how can I specify it? There are so many authors, many of them are good. So there are so many ways of expressing things. You could have your own way of expressing a thing. But yes, it must be proper, coherent, and error free. Yeah. So why don't you? Would you not consider that as a exercise that you are doing every time? Just not writing out the proof, but trying to explain what you are doing. Yeah.
Yeah, that's fine, Doc. To me, I think the only challenge for me, hopefully by November, I'll be far more comfortable with LaTeX than I am now. I spend more time typing the thing in LaTeX than actually solving it on paper.
Yeah. What are you using for LaTeX?
Text Studio.
Text Studio. To be frank, I have never used this Text Studio. I don't know what does it look like even, but I see it says it's a LaTeX editor. And does it do WYSIWYG? Does it?
I missed that, Doc.
Does it do what you see is what you get? Is it a?
Yeah,
Yes.
that's what it does. Yes, what you see is what you get. I don't think so.
No, it doesn't.
It doesn't do that.
No.
Oh,
no, yes. It's not like a word
okay.
Document.
Okay.
word processor. No.
Oh, okay. Well, okay. Yeah, one thing I must say, it is the tech is obviously a little bit different from Word, in the sense is yeah, what you are, the difficulty that you are facing is possibly inside the learning curve for tech. So
It's just the learning curve. But I'm hoping that
yeah,
by November I should be far more comfortable than I am now.
yeah, yes. That's true. I think you should be able to, because I believe for even the HRM course also demands you writing your things in tech, right?
Yes, it does. I'm hoping to do it next year.
Oh, okay. As I see on the net, it says that there are, if you want a WYSIWYG or some such thing, there is something called GNU TextMax. It is freely available. And there's another on Linux, it's called Leaks. That's also, these are WYSIWYG editors as I see. But to be frank, I have never used them. And I don't know. And there is a paid subscription thing, which is often called a scientific workplace, which many of my colleagues also use, but they have to pay for it. So it's not free. There's a license, and I don't like copyrighted things, so I've never touched it either. So that's why I don't know them. I do it in a simple text editor, and I know LaTeX has initial steep learning curve, especially if you are not but however, if you have seen Python or Pascal like programming languages, you should see that it is very much similar in structure. So every environment comes like with a begin and an end thing, and everything works inside the environment. Even the environment has its own variables. So it's very much like Pascal or a Python kind of a programming language. So, but you are doing text. But I hope, yes, I think, Stanley, you shouldn't be very much bothered about tech. You should be able to, by November, how much is this? This is July. By end of November, you should become a little better.
I should think so. Yes.
Yeah, it is
Thanks.
not train smash kind of a thing. Yeah. It's not a big deal. It takes some time, but it's not a big deal. Yeah. Any other issues? Okay. If not, then we can meet next time. Yeah.
Thank you, Doc.
Thank you.
Good night.
Thank you,
Good
Doc.
night. Keep well.
Good night, Doc.
Good night.
Don't forget to post this on the internet.
Yes. I'll do it. I will do it. Yes, I have. I hope today there shall be a recording, because I recorded it. And yeah.
It's on.
Okay.
It's on.
Okay. Thank you.
Thank you.
Thank you. Thank you. Bye.
Thank you. Thank you.
Thank you.